Hello everyone, I, Avinash Kumar Chaurasia, a final year PhD student from IIT Bombay, will present our work Simmer, a rate proportional scheduling framework to reduce packet drops for service function chaining. Simmer's main aim is to improve the overall throughput over vGPU or Mig instances. This work is done in collaboration with VMware. Network function virtualization offers various advantages over traditional middle boxes built using ASICs. Few of the NFV advantages over ASICs include reduced capital or operational expenditure, flexibility of deployment, and ease of scalability. However, the performance of NFV deployment remains a major concern. The motivation behind the use of GPU for such virtual network function deployment or service function chain is its ability to provide higher throughput without increasing the hardware cost exponentially. In this work, we are using hardware-assisted virtualized GPU technology for service function chain deployment. The hardware-assisted virtualized GPU technology provides isolated GPU instances to each virtual machine, hence providing better security in comparison to container-based service function chain deployment. This is the architecture of hardware-assisted virtualized GPU technology. A single GPU is partitioned into multiple logical GPUs, and each of them can be assigned to VMs independent of each other. The memory for each GPU is statically partitioned. In last couple of years, NVIDIA introduced a new virtualization technology called Mig Mode. Similar to vGPU, it supports multiple GPU instances for the cloud. Mig and vGPU instances differ in how GPU cores are shared among the instances. In Mig, GPU cores are statically partitioned and assigned to each instance. However, in vGPU, all instances share the GPU core, and scheduler will be responsible for assigning the cores dynamically. To control the vGPU provisioning and scheduling, NVIDIA provides two knobs, vGPU profile and vGPU scheduler. vGPU profile determines memory allotted per vGPU and puts a constraint on the maximum number of vGPUs created out of one GPU. The vGPU scheduler schedules the VM's workload on the GPU in round-robin order. Currently, NVIDIA supports three schedulers: best effort scheduler, equal share scheduler, and fixed share scheduler. Out of three, best effort scheduler performs better for the VNF scheduling. The problem with NFV chaining over vGPU is the heterogeneous resource requirement of each VNF present in the chain. The vGPU scheduler schedules VM in a round robin on the GPU without considering the compute requirement of each VNF. Consider a scenario where a fast processing VNF is followed by a slow VNF in the chain. In such a scenario, slow VNF will drop packets already being processed by the last VNF, resulting in lower throughput. Ideally, GPU should be allocated to each VNF in proportion to their compute requirement, so that no packet drop occurs. To further support our theory, we conducted an experiment consisting of three VNFs of different compute requirements deployed on vGPUs in the form of chain. As we can observe from the table, NF2 drops the majority of packets. Among all the three NFs, NF2 is the most compute intensive and NF1 is the least compute intensive. But the gap between their processing speed is not considered by the scheduler, resulting in the queue getting full at NF2, which further results in a packet drop. The easiest solution is to modify the scheduler or replace it. However, the driver and virtualization software is proprietary, hence it can neither be modified nor replaced. With the help of this work, we want to achieve a rate proportional GPU sharing by the VNF by identifying the bottleneck NF of the chain and increasing its share of the GPU. In this work, we have used the best effort scheduler as the base scheduler because the best effort scheduler outperforms the other two schedulers. We also know from the previous works that the best effort scheduler uses active GPU workload as a meta information for scheduling the VMs. We leveraged this property to design a rate proportional framework. This is our Simmer architecture. Simmer uses SRIOV enabled network interface card and virtualization aware NVIDIA GPUs to provision the virtual machines. Each virtual machine hosts a single network function, and Simmer uses a DPDK to bypass the traditional TCP/IP stack inside a virtual machine. A Simmer module is present inside each virtual machine, and it has two main components, a congestion monitor and a rate controller. The task of congestion monitor is to keep track of the occupancy of network function receive queue of its corresponding network function. There is a threshold associated with each such RX queue, as we can observe from the figure, and the congestion monitor periodically checks this queue and sends a slowdown signal to a rate controller of the upstream NF when queue occupancy goes above the threshold. Similarly, it also sends a fast enough signal to the rate controller of the upstream NF when queue occupancy drops below this threshold. The rate controller controls the packet flow between the RX queue and the network function. It indirectly affects the kernel launch activity by controlling the packet flow between the RX queue and the NF. When the rate controller receives a slowdown signal from a downstream NF, it temporarily cuts the flow of packets from the RX queue to the NF. However, when it receives a fast enough signal, it switches on the flow of the packet. In coming slides, we will talk about the performance of Simmer, the improvement offered by the Simmer, the correct configuration required for best throughput, and we will also look into which one among Mig and vGPU instances offer more to a service function chain. This is our experimental setup, and it consists of Xeon Gold 5218R CPU, a 768 GB RAM, and NVIDIA A100 GPU, which consists of a 6912 GPU cores and 40 GB memory. The setup also includes a 25 Gbps SRIOV enabled NIC card. The virtualization environment is enabled by ESXi 7.0.2 hypervisor. Each VM is configured for 30 GB RAM and 8 vCPUs. We are using Ubuntu 20.04 as a guest operating system and DPDK 18.11 for kernel bypass inside the guest. This table shows all the profiles supported by A100 GPU in Mig mode. Each profile is configured to have a fixed isolated memory. Suppose a GPU is configured for A100-15C, then each VM can access a GPU having a 5 GB memory, and total of 7 such instances can be created from the GPU. Similarly, in case of A100-740C profile, a MIG instance is created with 40 GB memory and it occupies the whole GPU. A Mig mode offers heterogeneous instance creation from a single GPU as long as the resource requirement of each instance does not cross the total available resources. This table shows all the profiles supported by A100 GPU in vGPU mode. The memory column explains the amount of memory reserved per instance of the vGPU, and the last column explains the number of vGPU possible if the given profile is chosen. NVIDIA currently supports homogeneous vGPU instance creation from a single GPU. That is, if one vGPU is instantiated using A104C, then all vGPUs can only be instantiated with A104C only. The first experiment consists of the base performance of each network function that we will be using in any service function chain in the future slide. We have three network functions, NF1, NF2, NF3. NF1 is router, NF2 is IPsec, and NF3 is NIDS. The graph shows the performance of a network function when GPU is configured in vGPU mode versus Mig mode. The profile for each mode is chosen in a way such that whole GPU is assigned to one VM only. As we can observe from the graph, the performance of an NF using Mig mode GPU closely follows the performance of the NF using vGPU mode. And out of all the three network functions, NF2, which is IPsec, is the slowest network function and will act as a bottleneck NF if it is part of any service function chain. This experiment is done to find the effect of threshold settings on the performance of service function chain. First, we created a chain of three homogeneous network functions. From the graph, we can observe that for best throughput, threshold should be kept lower than 3.6 times of the GPU batch size, and reason for better throughput is reduction in packet drops, which is actually reduced to 0. The graphs is showing the results for one NF, that is NF2, but we found similar patterns for all the other two NFs. For the same scenario in a heterogeneous service function chain, threshold can be kept a little higher, but it should be kept below 4 times of the GPU batch size for best throughput and 0 packet drops. This graph explains the efficacy of the simmer by explaining how simmer improves the kernel launch for the bottleneck NF. Experiment consists of a service function chain of 3 network functions, and NF2, which is IPsec, is the bottleneck NF for the chain. We conducted the experiment with simmer modules enabled and disabled and found that simmer increases the normalized kernel count for the bottleneck NF and reduces it for the others. It implies that the simmer work as intended as it increases the GPU share for the bottleneck NF. Next, we measure the performance improvement in terms of throughput. To measure this, we created two types of chains, static chain and dynamic chain. In a static chain, the packet flow is fixed and all packets follow the same path, whereas in a dynamic chain, the packet flow is based on the table. The graphs represent performance for the homogeneous and heterogeneous static chains. And as we can observe from the graph, simmer indeed improves the performance considerably for both homogeneous and heterogeneous chains. The throughput improvement up to 29% can be observed from the graphs. We conducted a similar experiment for a dynamic chain. We created a dynamic chain by splitting the traffic to form two flows. 50% of the packet follows a path of 3 network functions starting from NF2 starting from NF1, then goes to NF2, and then it goes to NF3, whereas rest of the 50% of the packet follows the path of 2 network function starting from network function 2, and then it will go to network function 3. Similar to static chain, simmer improves the performance of both homogeneous and heterogeneous chains in a dynamic chain, and an improvement up to 23% can be observed from the graph. Since Mig is a newer technology in hardware assisted virtualization domain, we deployed simmer on Mig as well as to understand the service function chain performance on Mig. Though simmer improves the throughput in Mig mode as well, but the performance gain is lower in Mig compared to vGPUs. In Mig, performance improvement is observed only due to the reduced packet drops. whereas in vGPU mode, both reduced packet drops and better GPU core utilization contributes towards the performance gain. This is the Mig profile we have configured for the network function in which are forming the chain. So IPsec is using 320C Mig profile, which has 3 compute SM and 20 GB of memory. Because IPsec was the bottleneck NF, we have given it the higher configuration, but still the performance of vGPU is much better than the Mig performance. In summary, a service function chain over vGPU provides better utilization of resources along with memory isolation. A service function chain over vGPU suffers from suboptimal scheduling, and the scheduler, being proprietary, can neither be changed nor replaced. To solve this, we developed a simmer which schedules the network function on the GPU based on the compute requirement of the network functions. And with the help of experiment, we have proved that simmer indeed improves the throughput of the chain and reduces the packet drop for a static as well as dynamic chain. And it does not matter whether GPU is in Mig mode or vGPU mode, simmer performs well in both the modes. And in all the cases so far, service function chain performance over vGPU mode is far better than the Mig mode. Thank you.